Hi, good morning to one and all. My name is M. Balamurugan, working as assistant professor in the Department of ECE, Erode Sengunthar Engineering College. First of all, I would like to thank the Erode Sengunthar Engineering College for giving me the opportunity to present a topic in digital electronics. So, in this video lecture, we would like to see what are all the basic gates that are available and their truth table and their circuit diagrams, followed by a slight introduction for what is meant by K-map and what are all the types of K-map and what are all the types of Boolean function. So let us start with, we will like to see what is meant by logic gates. So, so to start with the logic gates, AND gate. The AND gate is also called all gate or nothing gate. The Boolean expression for the AND gate is nothing but A dot B is equal to Y. Here A is and B is nothing but the inputs and Y is nothing but the output. So in this one we apply different combinations for the inputs A and B. We start with like 0, 0, 0, 1, 1, 0 and 1, 1, and what are all the possible output by using this AND gate. We see the truth table here. The truth table is given by, we have A different values and for B different values and their corresponding outputs. The function of AND gate is nothing but simply the multiplication of the two inputs. When the two inputs are high, we will be having the output. When any one of the input is zero means we will be having the zero outputs. So this is simply called y equal to a dot b, which is the Boolean expression for this particular gate. This gate is called all gate. All gate means the two inputs has to be one in order to have the high output. Let us see how this output comes. You see here, when the two inputs are low, the low condition is also known as 0. So we apply 0 for A, we apply 0 for B. Let us see what is the output. Output will be, so output is also 0. Why? Because we are using AND gate. The next condition, we apply high input to the B. Let us see what is the output. The input to the A, which is nothing but L, is unchanged. Let us see the output. The output is nothing but low. Let us see the third condition. Third condition is nothing but the A input and B input are 1. So what is the output here? It will be high. Why? It is called multiplication. So when the two inputs are high means it will multiple 1 cross 1 here. So we'll be having the output here. So let us see the final thing. We will change the output to be too low, and when any one of the input is low means output will also be low. That is called AND gate. So it will be having output high when the input is high. That is the condition for the AND gate. Next we will see the OR gate. OR gate is nothing but addition gates. If A and B are the inputs, Y will be equal to A plus B. It is simply the addition of what the input you give to the logic gate. Now we will see the truth table for the OR gate. So here you see A and B different values are applied, like 0, 0, 0, 1, 1, 0, 1, 1, and the output, corresponding output will be the addition of the two inputs. 0 plus 0 will be 0, 0 plus 1 it is 1, 1 plus 0 it is 1, 1 plus 1 it is also 1. So in this one, the condition to have the output as 1 means the condition is simply any one of the input, that may be A or that may be B. Any one of the input has to be high to receive the high output. Let us see the testing procedure. You'll see here we apply both the inputs A and B are high. So the output will be the addition of the two inputs. So if you add these two, high plus high, we'll be having high output. The next condition is we change the input B to 0, that is L here. Let us see the output, it will also be high. Next, we will change both the inputs to low, 0 plus 0. So if we add 0 plus 0, you will be having output also 0. And the final case, we will change the B output to low, sorry, too high. So if we add these two, 0 plus 1, it will be also high. And the condition for the OR gate to output 1 is any one of the input has to be 1. Let us see the inverter gate. The inverter gate is also called NOT gate. In this one, only one input is here, and we will be having the output. And the Boolean expression here we can write as A bar, otherwise y equal to A dash. So whatever we give the input, it will give you the output as an inverted one, right? And this one is also called, you see here, if you add one more NOT gate here, we will be having what is the input you apply to the input as output. Okay, so if you apply A here, you will receive A bar. If you have another NOT gate here, A bar is applied to the next NOT gate, and the output will be equal to the same as the input, which is nothing but A here. Okay, and let us see the truth table for this one. Truth table is nothing but if you apply 0 here, 1 will come as output. If you apply 1 here, you will have a 0 as output. Next, the gate is nothing but NAND gate, and following the other gates will be the application of the previous gates we see. That is nothing but you see here, NAND gate is nothing but it is NOT gate added to the AND gate. It is called NAND gate. So Boolean expression for the AND gate is nothing but A dot B, and the Boolean expression for this NAND gate, which is nothing but A dot B bar. And A dot B bar can also be written as A dot B the whole bar. Okay, let us see the truth table here, which is nothing but the inverted output of the AND gate. Remember, the condition for output of AND gate is when both the inputs are high, means you will be having the high output. Let us see the truth table for the NAND gate. You see here, AND gate, which is simply the multiplication of the two inputs. When both the inputs are high, means you will be having high output. Whereas the NAND gate is nothing but the inverted case of AND outputs. So you see here, for all the zeros, you will be having all the ones, and for this particular one, you will be having 0 here. Okay. Next, we will see the next we test the NAND gate. So here you see here we apply 0 0 here. So if we apply 0 0, the output will be high. Next case, we apply 0 1 here. In this case also the output is high. Next, the third case, we apply 1 1 here, and the output is 0. And finally, we apply 1 0 here, and the output is high. Okay, so here the output is low when both the inputs are high. That is the statement here. Okay, let us see the next gate, which is nothing but NOR gate. NOR gate, in the sense you will be having OR gate, and in the output you will be having one more NOT gate. And what is the Boolean expression for the OR gate? Which is nothing but addition of the two inputs A plus B, and the output of the NOR gate will be Y equal to A plus B the whole bar, or A plus B the whole dash. So here, what is the output here? If you let us see the truth table to see the output conditions of the NOR gate. So here you see, for both OR gate and NOR gate, the inputs and outputs are presented here. The output of the OR gate will be 1 if you have any one of the inputs are high. okay, or any one of the inputs are 1. So OR gate is nothing but the addition of the two inputs. Here it is 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, again 1 plus 1, 1. And the NOR gate will be the inverted case of the OR output. So if you have 0 here, you will have 1 here, and if you offer all the remaining ones, you will be having zeros here. So let us see the testing procedure. You see here, we apply 0 0 for AB, and the corresponding output will be high. Next case, we apply 0 1 here, and the corresponding output will be low. And the next one, we apply 1 0 here, and the output will also be low. And for the last one, we apply 1 1 here, the output will also be low. So here, what is the case for the output to be 1? The input has to be 0 0, and you will be having the unique output. Unique output, that means output is high when all the inputs are low. You see here, this is the case for unique output. Next we will see the XOR gate. XOR gate is also called exclusive OR gate, which is simply an Boolean expression for the output is given by y equal to a XOR with b. This gate is also called anything but not all gate. Let us see the truth table for this particular gate. Why? Because this is a special gate. That's why it is called a exclusive OR gate. So exclusive OR gate, in the sense, we will see the expression here. You see here. So this one, OR gate outputs are here and the XOR gate outputs are here. The Boolean expression for this particular gate is nothing but A bar B plus B bar A. That is the Boolean expression for OR gate. Let us see the Boolean expression A XOR with B. Okay, that is nothing but A bar B plus A B bar. So here, what is the output condition means any one of the input has to be high if you want to have the high output, and when both the inputs are low, the output will be low. When both the inputs are high, the output will be high. So this is the condition for the exclusive OR gate. Now let us see the testing. We apply we apply both the inputs are low, the output will be low. And the next thing, we change any one of the input to be high, we will be having the high output. When all the inputs are high means the output will be low. If any one of the input goes lows means the output will be high, right? So what will happen for the XOR output will be high when odd number of inputs are high. That is the case here. You see here, here we apply 1 to this input, and here also we apply 1 to this input, and the output will be high. That is nothing but here the input is only 1, whereas the two outputs are 0. Here also the input is 1, whereas the two other inputs are 0. We will be having the high output. That's why here it is given as when odd number of inputs are high, the output is high. Next we go to see the NOR gate. Here it is a complicated combination of XOR gate and then XNOR gate. So here XOR gate is nothing but when any one of the input is high means we will be having the output. Correct? When both the inputs are low, the output is low. When both the inputs are high, the output is 0. XNOR, in the sense a NOT gate is added to the output of the XOR gate. So when you have 0 here, you will be having 1. When you will have 1 here, you will be having zeros. So this is simply nothing but A XOR B, the whole bar. Let us see the Boolean expression for this gate. So here you see, this is the expression for the XOR gate, A XOR with B. if you apply the whole bar, which is nothing but XOR gate. Here the NOT gate at the output of the XOR gate is specified by the bubble. This bubble represents the NOT gate at the output. Next, we will see the K-map here. When you are trying to apply or implement a logic circuit with the help of logic gates, you will be having lot of terms that are present in the Boolean expression. So before getting into the K-map, let us see. Let us see one more thing. That is nothing but logical forms. Logical forms is nothing but how to represent a Boolean expression. So in terms of the Boolean expression is considered, we'll be having two types of forms, that is called sum of products, and the next is called product of sum. And what are the terms that are present in any of those forms? They are called as min terms for all the terms which are present in the sum of products, and the terms which are present at the product of sum are called the max terms, right? Canonical forms are nothing but simply standard forms for Boolean expression. Let us see what is those canonical forms, SOP and then POS. Let us see here. First of all, SOPs are explained. SOP is simply nothing but sum of products are called SOP, product of sum are called POS. And sum of products terms are called min terms, and the terms which are present in POS are called max terms. Let us see the expression here. Here A, B, C, three inputs are applied. Okay. And the outputs is nothing but F. Okay. And here one Boolean expression is given as F, followed by, you'll be having expression like A bar B bar C plus A bar B C, A B bar C, A B C bar plus A B C. And for if a term is bar, it will be 0. If it is not bar, if it is not having no bar or inverted, that will be 1. For example, if it is A means 1, A bar means 0. So for similar case, you see here A bar, B bar, C. We can write that as 0, 0 and 1. For the second term, A bar BC, that will be 0, 1, 1. And for the third term, A B bar C, that will be written as 1, 0, 1. And this particular term, A B C bar, that will be 1, 1, 0. And the last one, A B C, that will be triple 1. And you see here 0, 0, 1. The output will be 1. And for 0, 1, 1, the output will be 1. And you see here 101, the output will be 1, and the next one 110, the output is 1, and for the triple one the output is 1. That means what are all the possible cases of inputs that are present in this particular equation, the output will be 1. Here we will be having 1, 2, 3, 4, 5 terms, so and the output will be 1 for all the terms that are present in this particular equation. And for the all other inputs, that is 000, and then 010, and then 100, all those outputs will be 0. And in SOP we are already said the terms that are present in this particular thing are called min term. So in this one we will be having 5 min terms that are available. Okay, you see here the min terms can also be written as in this format also. F of A, comma B, comma C. A, B, C are nothing but the inputs. You see here A, B, C. And the output terms, the min term specified by the summation symbol followed by a small m. And 1, 3, 5, 6, 7. 1, 3, 5, 6, 7 are nothing but the min term numbers. That is nothing but, here you see for 1 we write m1, and for 3 we write m3, and for 5 we write m5, and for 6 we write m6. and for the 7 we write M7. Okay. And if you want to see what is the M1, you see here for A, B, C, the possible number of inputs are written starting from 000 to 111. That is 000, 001, 010, 011, 100, 101, 110, 111. And those numbers for all these inputs are given here separately. Okay, it will start with 0 here, and it goes up to 0 m1 m2 m3, and it goes up to m7, right? So this is called shorthand notation, right? So by using these numbers we can identify what are all the things will be having the output as high. Okay, in this case we will be having 1 3 5 6 7, and for all these five terms we will be having high output, and for the remaining other terms we put zeros. Okay, let us see the other case, which is called product of sum, and the terms that are present in this particular equation are called max term. Product of sum, in this sense, a term will be having all the addition of inputs. You see here it is, for example, a plus b plus c, and the second term is a plus b bar c, and the last term is a bar plus b plus c. And for this particular expression we will be having three terms, and for these three terms we will be having high output. You see here again the truth table is presented for three variable. We start with a b c, that is nothing but starting from 0, and it goes up to 111. And what are all the terms that are present here, what are all the terms that are present here, we will be having high, sorry, what are the terms that are present here, we will be having zero output. That is the reverse case. In case of SOP is considered, we will be having high output here, and for the terms that are present in POS, we will be having zero outputs. That you have to remember. And what are all the terms that are present in this particular expression are called max terms. And if you want to see the SOP means, here you see the SOP, right? And each term is called a min term. And for the term that are present in this Boolean expression, we will put 0, sorry, we will put 1 for SOP. Okay, and we will put 0 for POS. That you have to remember as a separate concept. Okay, here the max term shorthand notations are presented. Again we will be having the inputs A B C, which starts from 0 000 to 111, right? And their numbers. Max term is specified by capital M. It starts with 0 and it goes up to 7, right? And how we can write the notation here? For 000, we will be having A plus B plus C. For 001, we will be having A plus B plus C bar. And for 010, it will be A plus B bar plus C. And for 011 it will be A plus B bar plus C bar. Here you have to remember the concept. If it is 0, you have to put A. If it is 1, you have to put the bar. Okay, that is the reverse case. And the symbol for the max term is specified by pi here, and then capital M, right? For example, we will consider one variable, that is, sorry, one Boolean expression f of capital A, capital B, capital C, which is nothing but the inputs that are specified. And here one example is given, pi m of 0 comma 2 comma 4. 0 means it will be m0, 2 means it will be m2, 4 it will be m4. So you see here m0, what is the term here? A plus B plus C. Here it is written. And for the second term it will be A plus B bar plus C, and for the last term M4 it will be A bar plus B plus C. Okay, fine, let us see how we can convert the terms that are present in SOP to POS. As first thing, here we will consider one expression for SOP. Here one example expression is given, f bar equal to A bar B bar C plus A bar B C bar plus A B bar C bar. Okay, let us see how to convert this particular Boolean expression to POS by applying De Morgan's rule. By applying De Morgan's rule is nothing but you have to apply the inversion for the all the terms that are present here. You see here A bar plus B bar plus C bar plus A bar B C bar plus A B bar C bar, the whole bar. Okay. So if you apply the whole bar according to the De Morgan's rule, this SOP will be converted to POS like this. For example, you see here A bar B bar C bar. You have to apply inversion, which is nothing but A B and C. So the first expression A bar B bar C bar is converted to A plus B plus C, and the second term A bar B C bar. Here you see for A bar A is there, for B B bar is there, and for C bar it will be C. So it will be A bar plus B bar plus C. Similarly, we can write the inverted form for the third term. There is nothing but A B bar C bar. It will be A bar plus B plus C. Okay, so this is how to convert the SOP to POS. And we can do the reverse thing also. That is nothing but POS to SOP conversion. One example expression is given here: A plus B plus C bar, A plus B bar plus C bar, A bar plus B plus C bar, and A bar plus B bar plus C bar. Let us see how to convert. Again, we are going to apply the De Morgan's rule to convert that POS to SOP. So applying De Morgan's theorem means the whole term has to be get inverted. I will tell how to convert the first particular term. Here you see A plus B plus C bar is converted to A bar B bar C plus second term A bar, and for B bar B will come, C bar C will come, and for the third term A bar A will come, for B B bar will come, C bar C will come, and for the last term for A bar A will come, for B bar B will come, and for C bar C will come. Right? That's it. Let us see what is meant by K-map. We will come back to the K-map here. So now we understand what is Boolean expression and what are the types of Boolean expressions that are available. That is nothing but SOP and then POS. So if you take a Boolean expression means too many terms that will be there as a Boolean function, right? And for each particular term that are present in the Boolean expression, that are called literal, and K-map is a special map method which is used to reduce the number of terms that are present in the Boolean expression. For example, if you have A, B, C in the Boolean expression, you have to go for one AND gate, and if you have A bar B, C, you have to go for another AND gate. And by using this particular K-map method, we can reduce the number of gates. So by reducing the number of gates, the time required to design a logical circuit is reduced. By reducing the time, by reducing the number of gates, it will save you the cost also. And the design cost is majorly reduced by using this particular K-map. So if you take the different types of K-maps is considered, we will be having two variable K-map, three variable K-map, and four variable K-map. Let us see, for example, how to draw a K-map for a two variable. Here, minterms are presented here, and the two inputs here they take xy. Okay, up to till now we take the inputs as ab. Here it is changed to xy. For xy, we can apply both type of inputs as different combination. See here 0 0 0 1 1 0 1 1. So for 0 0 we can write the minterm as x bar y bar. For 0 1 we can write x bar y, and for 1 0 we can write x y bar. For xy, for 1 1 we can write xy. Okay, if your term is 0 means we will put the bar, if your term is 1 means we will put x. That is the thing. And for here the truth table is given for three variable. We start with x y z. Okay, that is 000 to 111, and their corresponding minterms are presented here. For triple zero, it will be x bar, y bar, z bar. For triple one, it will be x, y, z. And for all the remaining inputs, we can write the minterms like this. Okay, let us see the two variable. Let us see how to draw the two variable Kmap. Right here, you see we take the AND gate. For AND gate, the output will be 1 when both the inputs are 1. Here, the inputs are presented. Here, the outputs are presented. So here the output is written as f of x comma y equal to xy. That is nothing but x is input and y is input. We have to multiple the two inputs, right, to get the output. So here the output is 1 when both the inputs are 1. Let us see how to draw the two variable Kmap. So this is called two variable Kmap. In one side we write one input and the other side we write the other input. And here you see if you write x here it will be 0 1 and for y the 0 1, right? So you see here for 0 0 the output is 0, for 0 1 the output is 1, and for 1 0 the output is 1, and for 1 1 the output is 1. So here we have plotted the two variable Kmap by using this particular truth table. Let us see how to write this particular output equation. So by reducing the Kmap, we can write the Boolean function. So here you see we have to simply group the number of ones that are presented in this particular two variable map. That means here it is 0, you will be having 1 here, and you will be having two ones here. We have to combine maximum number of ones. Here you see two ones. Okay, this is one way of mapping, and this is another way of mapping. Let us see in the next slide. You see here, this is one vertical group is there, and you will be having another one. So one horizontal group will be there. Let us see how to write the equation for this particular thing. So if you take 1 1, okay, you have to see here 1 is presented, which is nothing but y. And if you take the horizontal input 1 1, you will be having 1 here. So here we can write the output as 1. So since the two groupings are available here, for this group the term is y, and for this group the term is x, and the expression will be f equal to x plus y, right? There are no other possible groupings are there since you have only 0, right? Let us see the example for three variable Kmap. For three variable Kmap, here we have to take one input here x, and the other two inputs are y z here. So for x the input will be 0 1, and for y z the different combinations like 0 0 0 1 1 1 1 0. Here you have to remember the last two columns are interchanged. After 0 1 you have to write 1 1. Okay, you cannot write 1 0 after 0 1. That you have to remember. These two columns are interchanged. And what are the possible cases of inputs? Here you see 0 0 0. That means x bar, y bar, z bar. And for 0 0 1 means for x it is bar, and for y it is bar, and for z it is 1. So here we can write x bar, y bar, z. Okay, so by using this schema we can fill the terms, right? Let us see one example. Here we consider one Boolean expression. Okay, f of x comma y comma z equal to x bar y bar z. So it is x bar y bar z plus x bar y z plus x y bar z plus x y z. Let us see how to fill this truth table first. So what is the first term is available? 0 0 1. So 0 0 1. We will put 1 here. X bar y z. So x bar y z means x bar means 0, YZ means 1 1. So here we put 1 and another term X Y bar Z. So for X we will be having here and then Y bar Z. Y bar Z means 0 1. So that will be 1. And for the last term X Y Z, X it is 1, Y Z it is 1. So here it is another one is present here. Let us see how to obtain the equation. We have to group maximum number of ones. The number of ones that are present in this map is nothing but 4 1. Let us see the grouping. So here you see four number of ones are mapped here and how we will write the equation that matters. So you see here four number of ones are available. So we can write the output f of x equal to how we can write here. If you consider x means 0 1, it is changing. We cannot write anything. And here the number of ones are present here and here. We have to compare these two variables. Okay, you see here for y it is 0 here and for z y it is 1 here. That means y is changing from 0 to 1. We cannot write anything. And here 1 1 is there. So if it is a same variable 1 1, that is nothing but z that we can write here. Okay, z. If it is also changing, for example, here you see z is changing from 1 to 1, that we cannot write. If you have 1 1 y, that we can write. That means if you have to compare the two columns, you have to check for the same value. For example, if you compare these two columns, right? If you compare these two columns, check the values. Here it is 0, here it is 0. So y is same. So we can write y bar. Okay. Here it is 0, here it is 1. It is changing. So we cannot write. Okay. And if you take these two column means 0, 1, it is changing. So we cannot write anything. You have 1 here and you have 1 here. That is nothing but Z. Okay. If you compare these two columns, right? 1 you have here and 1 you have here. So you can write Y. For Z is changing from 1 to 0. You cannot write anything. So another example for k variable, Kmap is nothing but 4 variable. So 4 variable Kmap in the sense it is called a 16 min-term Kmap. That is two inputs wx are written here and other two inputs yz are written here. So it will start with 00 to 11. Here also it will start with 00 to 11. So while writing, you have to remember 0001. So after this 01, you cannot write 10. Instead of 10, you have to write 11. And then their corresponding min terms are presented here. For example, 0000, we can write w bar, x bar, y bar, z bar. And for the other terms, 01 means here it is 00. So you can write w bar, x bar here. And here it will be y bar, and here it is z. So if your term is 0 means we have to put bar. If your term is 1 means we have to write Z. Simple. Let us see one particular example for this 4 variable Kmap. Let us consider this Boolean expression for w, x, y, z and the terms that are present here. W bar, x bar, y bar, z bar. W bar, x bar, y bar, z. W bar, x bar, y, z bar. Like this, almost 6 terms are presented here. 7 terms are presented here. So we have to mark all the ones in the Kmap by referring this particular equation. You see here, this is a 4 variable Kmap. So 2 inputs are here and the other 2 inputs are here. First you have to check 0 0 0 0. I means 4 0, that is 1. And for the second term, 0001, 0 0 0 1, that is 1. And for the next one, 0010, 0010, that is 1. And for the next one, 0110, 0110, that is 1. And for the next one, 10001, 1001, that is 1. And finally, 1010, that is also 1. Let us see how to group this particular number of ones. You see here, this particular number of ones, how to group all these things and then write the equation. You see here, in one column all the number of ones are present. This is another example for Kmap. Okay, and let us see how to write the output equation for this particular Kmap. Okay, and if you take this particular column means you will be having all number of ones here, and if you take this two column means you will be having two number of ones here, and you are having one particular term one and another one is here. So first we write the term first we write sorry first we write the equation for this particular grouping. If you take this particular of grouping, you will be having four number of rows to compare. So we cannot write any equation based on this one. So you have to go for this particular column. It is 0 0. So if it is 0 0 means you have to write dash for the corresponding variable. Y z are the inputs that are present. So first term we can write y bar z bar, plus we can go for the next particular term we can go for this particular thing. Okay, here you see it will be 0 1, but as 0 you have to put the bar, and 1 you have to simply write as it is. 0 we have to write w bar, 1 we have to write x. So it will be w bar x, and the ones are present here in this column and also in this particular column. So this column and this last column you have to check. First column and the last column you have to check. Here we have to see for the same variable. You see 0 first term, here it is 1. So y is changing from 0 to 1. We cannot do with that. So the second term we have to see. So here it is 0 and here it also 0. So corresponding variable is z. Since it is both the columns are 0, we can write z bar. So the term will be w bar x z bar, right? And for the next one, next possible number of grouping, this is nothing but 1 1. Here two rows we have to check, first row and then second row. So first row second row if you check means 0 0, it is same, and the second variable is changing from 0 to 1. So we cannot write for the second variable, we can go for the first variable, it is 0 0. So if it is 0 0 means we can write w bar, and here since the column is present is only one, we can write the variable as y z. Since we have 1 1 here, we can write y z, and the term will be w bar y z. Next possible case, that's nothing but don't care condition. Don't care condition is nothing but the output we cannot decide. For all the inputs that are applied to a particular circuit, we cannot decide the output. So what are the possible number of cases that you don't have the output, don't predict the output? We can write the condition as don't care condition, right? So here for the Boolean expression, what are the terms that are present? We can write 1, right? And for some terms, it will be marked as cross. So these are the cases for which we cannot decide the output whether they are 0 or 1, right? So these don't care conditions are also helpful in reducing the Boolean expressions. While grouping the maximum number of ones, we can consider these don't care conditions also. So here you see only two ones are presented, and in addition to that particular two ones, we can add these two don't care conditions also. So this is one particular grouping, and this is another one particular grouping. So for this particular grouping, all these values are changing, so we cannot write any term for these particular changing values. We can see 0 0 here, so we can write w bar x bar, and you will be having another possible case which is nothing but this one. Here also the values are changing, and this particular column value 1 1, which is nothing but y is it that we can write. Okay, so by using the don't care conditions also, we can reduce the K-map. So by this last slide, I would like to conclude my presentation. So in this, what you have seen means, what you have seen means the basic logic gates we have finished, and what are all the types of gates that also we finished, and what is Boolean expression, and what are all the types of Boolean expression like SOP and then POS, and how to write the term in SOP and how to write the term in POS, that is also seen. And by using De Morgan's law, how to convert a particular expression from SOP to POS, that is also over, and from POS to SOP, that is also over. Thank you. See you in one more class.